This is part 3 of the Calculating the Abundance of Isotopes Using Algebra lesson. In parts 1 and 2 we learnt how to approach these calculations and we saw some examples for elements with just 2 isotopes. In this lesson we'll see how to approach questions that involve more than 2 isotopes. The learning outcome for this lesson then is to learn how to adapt the method you used in parts 1 and 2 of this lesson to calculate the abundances of more than 2 isotopes of an element. Now for the specific examples that we're going to look at here, you'll already know the abundance of one of the isotopes. There are other ways that you might need to approach these questions where you don't know the abundance of one of the isotopes, but we'll look at that in the next video. For now, we're sticking with examples where we already know the abundance of one isotope. So let's see what we know so far and what still works and what we'll need to tweak a little bit to account for the extra isotopes. So what still applies is we'll use the same expression, the relative atomic mass is equal to the sum of the mass times the abundance. We'll still assume that the total abundance is 1. We'll still solve for x, and we'll still come back at the end and answer the question by using x to work out the abundance of the other isotopes and remembering to convert to percentage or whatever else we've been asked for. What doesn't work anymore, unfortunately, is the idea we've been using that the abundance of one isotope is x and the other's 1 minus x. I mean, of course, this is not going to work when you've got more than 2 isotopes. This is the bit then we're going to have to tweak and that we'll have to adapt to make it account for the other isotopes we have. Now, no matter how many isotopes you have, you're going to have to use algebra to represent the abundances so that you can work out an expression to use. How you do this depends on what information you've been given in the question. To some extent, this is where you're on your own, really. There are so many ways that these questions may be worded, and you're just going to have to use the ideas that we've learnt so far, along with your problem-solving skills, to work out an approach. But there's 2 main sets of data that you're likely to get for these questions, so we can at least learn an approach for each of those data types. And it might be that you know the abundance of one of the isotopes, and remember that's what we're looking at in this video. It might be instead that you know the relative abundances of 2 or more of the isotopes. Now that's what we're going to look at in the next video. Here's our first example question then. We have the hypothetical element A, which has 3 isotopes. One has a mass number of 2, one a mass number of 3, and the other a mass number of 4. And we're told that the abundance of the A2 isotope is 0.2. We're also told the relative atomic mass is 3.50. Now we're going to calculate the abundances of the other 2 isotopes. Remember, the total abundance is still 1, and remember we need to use the equation the relative atomic mass is equal to the sum of the mass times the abundance. Now, what we need to do is work out how we can represent the abundances of all of the isotopes using algebra then. Starting with A2, this is pretty straightforward. We told this, so 0.2 will be the abundance for A2, that will go into the equation. Then we're going to say that the abundance of A3 is x. Then for A4, bearing in mind the total abundance is 1, we'll do 1 minus the 0.2, which is the abundance of the A2, minus x as well, which is the abundance of the A3. So we're basically just working out the difference between 1 and the abundances of the 2 other isotopes, because that will tell us the abundance that's left over, and that will belong to A4. Looking at that, the 1 minus 0.2 minus x though, it looks a little bit clumsy, and we always want to keep the maths as simple as possible. So we're going to simplify that already, and if we do 1 minus 0.2, that gives us 0.8. So we can make this 0.8 minus x instead, and that'll just keep the expression that we end up with a little bit simpler. On to the expression then. Now we have the abundances, we can work out the expression, and we've done this quite a few times now, so I'd like you to pause the video and give this a go yourself. Let's see if you can come up with an expression. When you've got something to check, restart it and we'll have a look. So have you got something? Well, let's compare it to what I've got. I got 3.50 equals 2 times 0.2 plus 3x plus 4 times 0.8 minus x. And where I got that from, remember, was that the mass was 2 times its abundance, the 0.2. The mass of the second isotope was 3 times its abundance, which is x. The mass of the fourth isotope is 4 times its abundance, which is 0.8 minus x. We now have the expression then, so we need to go ahead and solve for x. It does look a little bit more complicated, the expression that we have here, than we've seen before, but the steps that you're going to take to solve for x will be exactly the same as the steps that you've taken previously. So pause the video and let's see if you can give it a try. Now, once you've got your expression, I'd like you to go on and calculate the abundances of the isotopes A3 and A4. How are you doing then? If you're stuck at all, remember your 3 steps for solving for x. First one, expand the brackets. Secondly, combine the like terms. Then simplify and solve for x. Let's see how we approach this then. If you've worked out x, we'll check your answer and see if you're right. If you don't have an answer and you're a little bit lost, don't panic. Just make sure you can follow along with my working and then come back and have a go by yourself afterwards again. Okay, so to solve for x, my first step, I started by expanding the brackets as usual. So I do 2 times 0.2, then I do 4 times 0.8, then 4 times minus x. And when I've done all of that, I end up with 3.50 equals 0.4 plus 3x plus 3.2 minus 4x. And I got the 0.4 from doing 2 times 0.2. I got the 3.2 by doing 4 times 0.8, and of course the minus 4x, comes from 4 times minus x. Next step, to combine the like terms, so I'll combine the x's. So 3x minus 4x leaves me with 3.50 equals minus x plus 0.4 plus 3.2. Now I need to simplify the expression, so I'll do 0.4 plus 3.2. And here I am, I've got 3.50 equals minus x plus 3.6. Finally, if I subtract 3.6 from both sides, there we are, that'll leave me with minus 0.1 equals minus x. And that means that x is 0.1. Now we have x then, we need to make sure we actually answer the question, so let's do that. So the question asked us to calculate the abundances of the isotopes of A. We already had the abundance of the isotope A2, which was 0.2. We said that the abundance of A3 would be x, and the abundance of A4 is 0.8 minus x. Taking what we've just calculated then, the abundance of A2 is 0.2, as we know. Given that A3 was x, its abundance is 0.1. And given that the abundance of A4 was 0.8 minus x, we're now left with 0.7. And here are our abundances, 0.2, 0.1 and 0.7. And you can see they add up to 1, so that maintains that rule of the total abundance being 1. Okay, let's think about what we've just been doing then, and let's see if we can add a rule that will help us out with this in future. So if you have 3 isotopes and you know the abundance of one of them, you need to decide how you're going to represent the abundance of the other 2. For one of the others, make it x. For the third isotope, you can do 1 minus the abundance of the first isotope minus x, but remember to simplify this. So for example, we had 1 minus 0.2 minus x, which we simplified to 0.8 minus x. We now have a way of approaching these questions though, but before we see an example, remember this is contingent on the abundance being 1. So your abundance needs to be a decimal. If it isn't a decimal, you need to convert it to 1. Now we'll see an example where you'll need to do this for the next question, so be ready to think about this there. And here is your next question. This time we're looking at the isotopes of magnesium. Magnesium has the 3 isotopes you can see there. The abundance of the magnesium-24 is 80% and the relative atomic mass is 24.3. I want you to now pause the video and put everything that you've learnt into practice. And restart it when you're ready to check the answer. Have you got something? Well, let's check it. So for this question, you can see that you were given the abundance of magnesium-24, but you had it as a percentage. And as we talked about earlier, you'll need to convert it to a decimal. I'm hoping you picked up on this then. Now to convert to a decimal, all you're going to need to do is just the 80% divided by 100, and that gives us 0.8. So where we are now is we have the abundance of magnesium-24 as 0.8. We then need to work out the abundances for the other two isotopes. Now magnesium-25, we're going to say that that's X. And that means the abundance of magnesium-26 will be 1 minus the 0.8 minus X. That will simplify down to 0.2 minus X. So we now have a way of representing the abundances. Let's put them into an expression. And here's the expression I got. 24.3 equals 24 times 0.8 plus 25x plus 26 times 0.2 minus x. From there, we need to solve for x. As always, we'll expand the brackets. That leaves us with 24.3 equals 19.2 plus 25x plus 5.2 minus 26x. Combine the x's by doing 25x minus 26x. That gives us 24.3 equals minus x plus 19.2 plus 5.2. We want to then do 19.2 plus 5.2 to start simplifying this a little bit. That leaves us with 24.3 equals minus x plus 24.4. Then we subtract 24.4 from both sides. And when we do so, that leaves us with minus 0.1 equals minus x. Now you can see we've got 0.1 for x again. We had that in the last example. Now don't be suspicious about this, it's just that the abundance of 0.1 is quite a common abundance for isotopes, so you will often see this. Okay, still haven't answered the question though. Let's go ahead and do that. Now, magnesium-24, we know the abundance for that was 0.8. We know that magnesium-25 was X, so that's 0.1. Finally, for magnesium-26, the abundance will be the 0.2 minus 0.1 equals 0.1. So the abundance of each of the isotopes is actually 0.1. And to get these as percentages, we'll times them both by 100, giving us the abundance of magnesium-25 and magnesium-26 being 10% each. Now we're nearly done with this lesson, but before we move any further, let's quickly talk about what we'd do if we had more than 3 isotopes. Again, this is the point where it really just does depend on what information you have. And it definitely is where your problem solving skills are going to come into it. But if you have more than 3 isotopes, it's likely that you'll have some information about 2 of the isotopes at least. Beyond that, the maths gets a little bit more complicated than you'd be expected to be able to do for A-level, and it just gets a little bit out of our remit here. So let's imagine that we do have that type of information. We do have information about 2 of the isotopes. Another hypothetical element, Z, has 4 isotopes, Z20, 21, 22 and 23. The abundance of Z20 is 0.3 and the abundance of Z21 is 0.1. Now bearing in mind everything we've been talking about before about making sure that the total abundance is 1, I want you to think about how you would represent the abundances of the other 2 isotopes. So stop and think about what you might do, restart it when you're ready, and then we'll see if your ideas are correct. Okay, so how can we represent the abundances of Z22 and Z23? Well, this is the idea that I had. I'm going to make Z22 X, and then I'm going to make Z23 1 minus the 0.3 minus the 0.1 minus X. What I've done there then is very similar to what we did with the 3 isotopes. You do 1 minus the abundances you know about and minus the X as well. And of course you'd want to simplify that a little bit, so that leaves us with 0.6 minus X instead. Okay, on to the next video then. The next video is the last video in this lesson, and what we'll look at there is how to approach questions where, rather than knowing the abundance of one of the isotopes, instead you'll know the relative abundances of 2 or more of the isotopes. So when you're ready, move on to that video and then we'll be done with this lesson very shortly.